People who often travel through time and space know that theoretically, wormholes can allow such journeys, taking you back to the time you wish to return to. Today, let's look at a thought experiment. A wormhole stretches from the orbit of the Moon to a vast empty region near Neptune. A welcoming ceremony has already been prepared there. To capture a wormhole from the depths of quantum foam, humanity has paid a tremendous cost in effort and resources, but general relativity had already predicted their existence, and now it has finally appeared. With this technology, human beings can at last realize the dream of interstellar travel. So after the final calibration and adjustments, the spacecraft and its brave crew entered the throat of the wormhole. They passed effortlessly through the spherical boundary of its entrance. Onlookers watched the spacecraft gradually recede, its figure shrinking smaller and smaller, as if gliding effortlessly toward its destination. At 4.12 billion kilometers away, the reception team could already see the spacecraft approaching. Its figure grew larger, bit by bit. Previous unmanned probes had taken about 30 minutes to cross this distance, and this manned spacecraft seemed to be following a similar path. But soon, whispers of concern rippled through the crowd. The spacecraft appeared to be slowing down. Finally, it stopped, as if frozen in place. 30 minutes passed. Still, the spacecraft did not emerge. Then days, then weeks, then months. High-precision telescopes stationed at both ends of the wormhole confirmed the spacecraft was still moving, but at a speed nearly imperceptible. Debates about what to do broke out. Should they send a rescue mission? Shut down the wormhole generator? But every option seemed destined to end in tragedy. For if the exotic forces maintaining the wormhole's stability fell even slightly out of balance, the ship and its crew would be torn apart. The only safe course was to wait. 500 years passed. At last, the wreckage of the ship slowly emerged from the wormhole's other side. It was still intact, but barely functional, a hollow shell. Over the ages, ravaged by the wormhole's brutal environment, the crew had long since perished. Their remains still strapped to the command chairs. The wormhole was finally shut down. Clearly, their calculations had been wrong. General relativity's predictions weren't enough. They had believed they had mastered the tangled frontier of gravity and quantum mechanics, considered every possible interaction, but something had gone fatally wrong, and humanity, staring at the distant stars, had never felt so alone. Wormholes are complicated. They do appear in the equations of general relativity, almost as old as the theory itself. But tragically, for those test pilots bound for Neptune, relativity was merely a machine, a device for describing how gravity works. In different scenarios, it did not guarantee that the universe would allow those scenarios to truly exist. So then, what would it take to build a real wormhole? What mechanisms could allow one to exist, and which would forbid them outright? Could they carry us to the stars we dream of reaching, or only hurl us toward a premature death? Critics called it chaotic, obscure, absurd, but to Edgar Allan Poe, it was his greatest work. In 1848, just a year before his mysterious death, Poe published this book. As a professional writer, he had spent much of his life in hardship. The success of The Raven gave him a rare moment of financial relief, and he used that moment to complete what he considered his masterpiece. He called it the one great purpose of my literary career. The book was Eureka. Its contents were sprawling, and today, nearly forgotten, far less famous than his poetry. But within its tangled lines were sentences far ahead of their time. In a chapter on interstellar space, Poe suddenly wrote, "Space and time are one." To Poe, there was no distinction between space and time. Nearly a century later, Albert Einstein, unaware of Poe's musings, revived the same idea of the long-dead New England poet. It was 1905, a year later known as the Miracle Year. In that year, Einstein published 5 papers, each profoundly reshaping our understanding of reality. One of them, perhaps the most important, discussed the relationship between motion and energy. It was in this paper that Einstein proposed special relativity, showing that measurements of length and time depend on the observer. But his former teacher, Hermann Minkowski, felt he had not gone far enough. Soon, Minkowski gave a geometric, intuitive explanation, describing the universe as a 4-dimensional whole. Unlike Poe's hazy intuition, Minkowski's spacetime did not mean space and time were identical, but that they were 2 aspects of one unified entity. Einstein once again learned from his teacher. He quickly embraced this idea, and with it, made another giant leap of imagination. In 1915, Einstein unveiled general relativity. In its language, spacetime is not static. It reacts to matter and energy. The unified fabric of spacetime bends under matter, and that curvature in turn guides matter's motion. Years later, physicist John Wheeler summarized it in one elegant phrase: mass tells space how to curve. Space tells mass how to move. This is happening all around you, even inside you. Ripples in gravity, gravitational waves, constantly stream in from catastrophic cosmic events, sweeping across Earth. As they pass, space itself is stretched and squeezed. If you could measure at the scale of an atomic nucleus, you would feel yourself gently elongated and compressed. Like Poe's words, general relativity is beautiful, mysterious, sometimes even incomprehensible. It is not just a theory of natural law. It is more like a machine. Give it a distribution of matter, and it will spit out an answer, predicting how that matter evolves under gravity. But relativity will not tell you whether such matter configurations actually exist in the universe. The decision of possible or impossible still rests with us. Newton's law of universal gravitation works similarly. Give Newton a distribution of matter, and his equations will describe its motion. But Newton will not answer whether the universe truly contains a 10,000 light-year metal rod. What makes things harder is this: general relativity is not as simple as Newtonian mechanics. It is not a single neat equation you can jot down in a high school classroom. It is a set of 10 equations in 4 dimensions, entangled and nonlinear, extremely hard to solve. Physicists know it is correct and practical, but most scientists prefer to study simpler problems in microphysics or astrophysics. As the famous G.G. Thomson once said, "I must admit, no one can clearly explain what Einstein's theory really is." Still, some breakthroughs were made. Shortly after Einstein proposed general relativity, Karl Schwarzschild, in the trenches of World War I, found a solution. He entered the simplest case, a matter distribution like the solar system. The result described the strength of gravity around the sun. But hidden within this solution was the possibility of a starting point. In other words, if a star were compressed below a certain limit, it would collapse endlessly, gravity overwhelming all other forces, forming a point of infinite density, surrounded by a one-way boundary, the event horizon. The relativity machine had done its job. What remained was to decide whether such an outcome truly existed. Most scoffed at the idea. Even Einstein himself, in a 1939 paper, denied it, believing no object could collapse to such an extreme. At the time, these hypothetical objects were called frozen stars. Einstein said they were impossible, but Robert Oppenheimer disagreed. Just months after Einstein's paper, Oppenheimer and his student Hartland Snyder continued their research. They had just calculated the maximum mass of neutron stars, the densest stars known, pushing beyond that limit. Their conclusion was the opposite of Einstein's. A star massive enough would inevitably keep collapsing to infinity. The relativity machine revealed what followed. The star would seal itself off from the outside world, leaving behind only a persistent gravitational field. But on the day their paper was published, Germany invaded Poland. War buried their discovery for decades. Oppenheimer himself was drawn into the Manhattan Project, never to return to these cosmic mysteries. Still, over time, the evidence grew undeniable. Black holes are real, but is that the full extent of relativity's predictions? Behind the Iron Curtain, in 1964, Soviet astronomer Igor Novikov saw something different. If you ran the black hole equations backward, a twin appeared. Novikov realized the math of general relativity does not care about the direction of time. Like a video of a ball thrown in the air, play it forward or backward, it looks the same. So too with gravity, he proposed. If black holes can swallow matter forever, then inversely, there could exist objects that forever eject matter. These were white holes. White holes have beginnings, but nothing can enter them. You would still feel their gravitational pull, but never cross their reverse event horizon. If you started inside one, you would be expelled violently, faster than light, until flung out completely. White holes would spew matter and radiation, until exhausted, leaving only a naked starting point, and its reversed horizon. They are black holes' time reflections. Most scientists dismissed them, but some were intrigued. Roger Penrose, later a Nobel laureate for his black hole research, realized that white holes might hold the key to another exotic solution, a tunnel to another universe. And the one who finally gave this tunnel its name, Wormhole, was his friend, John Wheeler. He discovered that black holes and white holes could be linked, and such mathematical knots had already been written down decades earlier by one of Einstein's assistants. This meant that some branch of relativity might truly allow humanity to cross the stars. But scientists still need to figure out, is this the prophecy of genius, or the fantasy of madness?